Right. So in this topic, we're going to explore chemical bonding, which is the capacity for atoms to link together. The chemical bonding comes in two major types. The first one is ionic bonding, and as you can see, table salt is one example of it. Here you see that there are two ions, sodium and chlorine, that form regular patterns, and they eventually form what we call a crystal. There is not an actual molecule that forms when you have ionic bonding. Instead, it's a repetitive sequence or pattern of the atoms themselves. The second major type of bonding is covalent bonding. Here you get the formation of true molecules, and what you have happening here is you have a sharing of the electrons to form these molecules. The third type of bonding, there are three of them actually. The third type of bond is referred to as metallic bonding. And what happens is these are all the same kind of atom, but these atoms sit in a sea of electrons that hold the structure together, and that gives it some very unique properties. So those are your actual three major types of chemical bonding, and in this presentation we're going to explore the first two, which are ionic and covalent. In the bonding of ionic or covalent, either you have a gain loss of electrons, which forms ions, or you have a sharing of the outermost electrons, and both these strategies are an attempt to fulfill the outer shell electron configuration. So what are the properties of these two main types we're going to look at? In ionic bonding, you have a complete gain or loss of electrons. In covalent bonding, you have a sharing of these electrons. In both cases, the atoms are going to do this in order to achieve a full outer shell to its electrons. When you do have a full gain or a loss, then the atoms become ions, pluses and minuses, and the atoms themselves are attracted to each other and hold together. This attraction is referred to as electrostatic attraction. The sharing of electrons in the covalent bond side, the sharing creates a link between the atoms. The result of the ionic bonding is you get a crystalline structure, not a discrete molecule, and you create what's referred to as an empirical formula for the crystal. When you do get covalent bonding, you get actual discrete separate molecules in the gas, liquid, solid state, and you actually have a molecular formula that's created. Now, what exactly is the nature of these bonds? We need to explore this in more detail. A gentleman by the name of Lewis, who was a professor at University of Chicago, he came up with a strategy to clarify what goes on during bonding in general and ionic and covalent bonding specific. And he developed what was called a Lewis dot structure. The Lewis dot structure is just a method of writing down and following the electrons during bonding. How does it work? Well, the Lewis dot structures show only the outside valence of electrons and show how they're arranged. And as you might suspect, there are dots, actual physical dots, used to represent these valence electrons. So what you see happening here is the sodium has one dot on the outside, and if you look up at the periodic table, you will notice there's one valence electron in that location. What about all the inner electrons around the the inner core? And the answer is you do not work with them. Instead, you only represent the outermost electron with a dot, and in this case, you are looking at the single one placed around the sodium. Look at carbon. Carbon up here on the periodic table, there are 2 inner core electrons and there are 4 outer electrons. And again, you would only represent the 4 outer electrons. You ignore the inner core. And finally, fluorine, you have the 2 inner core up here in the periodic table in black, but you have 1, 2, 3, 4, 5, 6, 7 electrons in the outer, which are represented. I show you these electrons as moving away to show you that there are the valence electrons that are placed around the symbol, in this case of fluorine. Now, let's take a look at how to draw the Lewis structure of oxygen. Oxygen has it has 2 electrons in the first shell, which is the 1s2. And then in the second shell, you have 2 electrons in the s and then 4 in the p. So the total number of valence electrons is 6, 2s and 4p. Now, if we were going to record the Lewis dot structure for this, that's how you would do it. You would have a total of 6 dots around the symbol O, which is oxygen, and notice we ignore the inner core electrons. You will also notice that the dots are placed in a very organized fashion. They're placed like a north, south, east, west compass. So it's nicely balanced all around. So if we now take a look at the periodic table, we can start to see how it would represent the different elements as Lewis dots. Let's begin at lithium, Li. It's in the upper left-hand area. Lithium has 1 dot because there's only 1 electron in the outside valence shell. And based upon previous discussions that we've had, sodium, potassium, rubidium, cesium, francium, all of them have 1 valence electron, therefore they all get 1 dot. Again, to re-emphasize things, the number of electrons in sodium, Na, the total number, is greater than what you see in lithium. But since we ignore the inner core electrons and concentrate only on the valence electrons, then lithium and sodium would each have only 1 dot. And as you work your way across, we see some interesting patterns. Beryllium, which is next to lithium, it has 2 dots or 2 valence electrons. Now notice, when we put those 2 dots or 2 valence electrons, we put them on opposite sides of the atom. Those electrons, as valence electrons, are going to be as far apart as possible. In boron, working our way across, notice we add a 3rd valence electron. Again, in a separate region, we do not pair them up. And finally, in carbon, there are 4 valence electrons, so we have 4 separate dots on the different locations around the atom. Nitrogen, we now have to go back and start to fill in a 2nd dot because all the separate regions have 1 already, so we have to double back. And you can work your way all the way to neon, which has a full outer shell. You have all 8 electrons on the outside. So here's your basic rules. Hydrogen and helium follow the duet rule. And what that means is hydrogen and helium must get to 2 valence electrons to be stable. Helium, as you might recall, already achieves this. It's a noble gas. Hydrogen does not and is unstable and will have to take steps to become stable. Now, if you take a look at all others, All other atoms follow the octet rule. And what that means is you have to have 8 valence electrons on the outside in order to be stable. If in fact the atom becomes an ion, which means it has extra electrons or has lost electrons, you put a bracket around that atom and you indicate the charge that it possesses. So let's take a look at this in action. Hydrogen has 1 electron. Now what it can do is it can give up that electron, give up the valence electron, and by doing so it becomes an ion, which is an H+. Notice the notation that is used to designate it as an ion. Another strategy is on occasion a hydrogen can gain the extra electron, filling the outer valence shell. In this case it's the duet rule, and you notice the use of the bracket and the negative charge to indicate that. Let's take a look at fluorine. Fluorine has 7 valence electrons. Notice we fill it all around. There's all 7, and that right there is called the Lewis dot structure for fluorine. Now, atoms need to have 8 electrons. Fluorine has only 7. It needs to pick one up, so it is considered unstable. So what has to happen is fluorine is going to gain an extra electron and become an ion, which is a -1. It's kind of counterintuitive, but atoms have no problem taking on a charge. In this case, fluorine, there's no problem being a -1. What is a problem is having a not filled valence shell. So stability is achieved, and it's not a problem becoming an ion. How do we represent it for compounds? So in order for a compound to form, all the atoms involved have to achieve the noble gas configuration. In other words, the outside valence shell has to be filled. Now, if atoms are going to share electrons, in order to do so, they'll form the covalent bond. We can show the shared pair of electrons by using a line. In this given case, what you notice is we got hydrogen, which has 1 electron, and fluorine has 7. The hydrogen is going to move over, and it's stable, because if you look closely, hydrogen has 2 electrons, fluorine has 8 electrons. Yes, those 2 electrons in between them count for both the hydrogen and the fluorine, therefore it's stability. But if we work with a different notation, we can write down a line to represent the single covalent bond. The line represents a sharing of the pair of electrons. Notice the other 6 electrons remain as pairs of 2, and they're not participating in a bond, but it still creates stability for the atom. So this compound is hydrogen fluoride, and it does form because all atoms have achieved a full valence configuration. So bonding electron pairs, they're involved in the bonds. They can share up to 3 pairs. That means that any given set of atoms can share or create 3 bonds or triple bonds. Lone pairs are the ones that do not participate. Now this is vocabulary that is extremely important, so make sure you understand what this is saying. You will notice that the hydrogen and the oxygen are sharing 2 electrons. That makes a bond between the hydrogen and the oxygen. Therefore, those 2 electrons are called bonding pairs. However, notice that there are 2 pairs of electrons around the oxygen that are not participating in any kind of bonding. Those are referred to as lone pairs because they are sitting separate and not involved in any kind of bonding. So let's now use Lewis dot structures and explore covalent bonds specifically. So the Lewis dot structure is a method of representing bonding, and in this case it's going to be a covalent bond. There's a very, very good internet representation of the covalent bond. Let's take a look at it now. They come together, and what happens is right here you get a sharing between the hydrogen and the chloride atom. And what you get is you get hydrogen chloride molecules created. Those hydrogen chloride molecules are what are found in gases or in liquids. They are simply bazillions of small molecules. Let's take a look at it again. We take a hydrogen atom and a chlorine atom. Hydrogen atom needs one more electron. Chlorine atom needs one more electron. They merge together and they share each other's electrons. That sharing is the bond. It is a covalent bond. We now create the molecule hydrogen chloride, and we can have lots and lots of them. When you take the hydrogen chloride molecules and put them all together, you can have the gaseous hydrogen chloride, or it could be existing as a liquid. Now, let's now take a look at the details of the covalent bonding. How many possible bonds can you create? And the answer is a maximum of 3. I mentioned that previously. Now remember, every line is one bond. To make one bond, you have to share 2 electrons. So the maximum is 3. So let's draw the Lewis dot structure of O2. So our strategy is as follows. We have 2 oxygen atoms. Each oxygen atom has 6 electrons around the outside. The total, therefore, available is 12 in order to build this molecule. The first thing we do is we connect the 2 atoms with a single bond. Then what you do is whatever's left, you put it around the other atoms. So there we have that bond between the oxygen required 2 valence electrons. One came from one oxygen atom, the other one came from the other oxygen atom. We have a total of 12 electrons to work with. So what we do now is we now distribute the remaining electrons around it. Notice we work with them in this case as pairs. And we ask the question, so did it work? Well, it fails because look at the first oxygen. There's 2 on top, 2 on the bottom, 2 to the side, and remember the bond it makes has 2 electrons count also. So that oxygen on the left has 8. It's stable. It fulfills the octet rule. Look at the oxygen on the right. There's 2 electrons on top, 2 on the bottom, 2 involved in the bond. So that's a total of 6 electrons. It's got to get to 8. So that right there is unstable. What else can be done? We can generate an extra number of bonds. So I need 2 more electrons. So I need 1 extra bond required. So here we go. Instead of having 1 bond between the oxygens, I create 2 bonds. Now I continue to fill in what is left. And now the question is this stable? Well, the oxygen on the left has 2 on the top, 2 on the bottom. Each bond has 2 electrons also that count for it. So that's 8. We do the same count on the other side, that's 8. So all atoms are satisfied in this molecule. So therefore, this is a successful structure. Now the way we represent this is at the bottom, you'll notice we can show 2 pairs of electrons between the oxygen, or we could simply create a double bond or double line between it to represent it. What if there's more than two atoms involved? The least electronegative is always in the middle, and you connect everything from there. So if you take a look at CO2, carbon is the least electronegative. It has the least draw of it. You might also note that often the central atom is the single one. So both methods often work. So if you count them up, there are 16 valence electrons. Your first move is to put the carbon in the central atom, build the other two, and link them together in single bonds. Notice, when you build those single bonds, there are 4 electrons that are removed from the pool that can be used. So, we always work to fill the outermost atoms first. So what you do is you put a pair down below there, a pair there, and a pair there. You put a pair around that oxygen, and that oxygen. All of our valence electrons have been accounted for. That's terrific. But now, is each atom satisfied? In other words, is each atom's valence shell filled? Well, I see 2, 4, 6, I see 8 electrons around the left oxygen, 2, 4, 6, 8 electrons around the other oxygen, but I see only 2, 4 electrons around the carbon because it has only 2 carbon bonds. So, it's not stable. All the atoms are not happy. So what we have to do is go back and figure out a way of doing that. So what we're going to do is we're going to take our 16 valence electrons, take our carbons, and what we're going to do is we're going to place it like before, but now watch this. We're going to take 2 electrons away from that oxygen and make it a double bond. Is everybody happy? No, and the reason why is if you count the electrons around the carbon, there's 2, 4, 6 electrons around the carbon because each bond is 2 electrons. I have a total of 6. So we have to do another strategy. Let's take 2 more electrons from the other oxygen and make another double bond. Is everything satisfied? It is. There's 8 electrons around the carbon because of the double bonding, and there's a total of 8 electrons around the oxygen. So this is what carbon dioxide would look like. What if the molecule itself is an ion? What if it's a polyatomic? So we're going to have to make sure that we use our bracketing when we do this, and we account for the charge. So let's take a look at this. CO3 minus 2. So carbon, as you can tell, has 4 valence electrons around it. Oxygen has 2, 4, 6, 2, 4, 6, 2, 4, 6. However, that's a total of 22. However, we have to account for the additional 2 electrons that this polyatomic molecule has. So it's not 22 valence, it's 24 valence electrons. So we have 24 valence electrons to work with, and we have to get every atom to have a full 8 electrons around it. So let's take a look how we're going to do this. Brilliant. Mr. Hollander is fantastic at this. So we've got 24 valence electrons, and there's our atoms. What we do is we put the carbon in the middle because it's the least electronegative. It's also a singleton. And what we do now is we automatically make a bond, and a bond. Each bond ties up 2 pairs of electrons. We're now going to distribute the rest of them around the outer electrons. Voila! You will notice that all of our oxygen atoms are completed, but the carbon itself has only 6. So each bond around the carbon is worth 2. We have only 6. How are we going to solve this? Well, what we do is we choose one of the oxygens and create a double bond with the carbon. But we do have one last mistake. Before I get there, let me make a comment on this. You will notice that we chose 2 pairs of electrons from that oxygen on the lower left to build our double bond. Couldn't we have used 2 pairs of electrons from the upper oxygen? Couldn't we have used a pair from the lower right ones? Yes, you could have, and it would have worked. But we chose to work by using the one on the lower left, though the other ones would have worked. But we still have a problem. Why does it fail? We have 8 electrons around the carbon, 4 bonds, and we have all the oxygen satisfied. It's failed because we didn't use our notation properly. When we build the Lewis dot structure here, we have to create the bracketing and the minus charge associated with it. Now we're in business. We're golden. What if there's more than one central atom? For example, carbon. Carbon here has, there's 2 of them. So what you do is you take the 2 carbons and you're going to link them together. We start by knowing that we have 16 valence electrons, and we link the 2 carbons together first. We then attach the other atoms to the 2 carbons. Could I reverse that? Could I have put fluorine on the left and hydrogen on the right? Absolutely. That order does not matter. What we then do is distribute what we have left. And we have a total of 16. 10 of them are left because 6 got tied up in the 3 bonds between the hydrogens, the carbons, and the fluorine. So let's distribute those now. 2 for the fluorine, 2 more for the fluorine, 2 more for the fluorine. Now, why are we loading up the fluorine? You load it up because it has the greatest electronegativity. Fluorine is now satisfied. If you add it up, we've got 6 electrons in the bonding, and we've got 6 more going for the fluorine. We have 4 valence electrons left. We'll put those around the carbons. But it's not going to work because we don't satisfy the carbon. What if we triple bond it? And the answer is that solves it. Notice that what we have is we have the bonding for the fluorine, the bonding with the hydrogen, and the bonding with the carbon. Now, can we do Lewis dot structures for ionic bonds? Yes, we can, but we'll pick that up in part 2 of the series.